friends, welcome to the series lecture of Mathematics 1. Up to last session, we have seen all topics of infinite series such as partial sum, then integral test, comparison test, root test, ratio test and Leibniz test for alternating series. In today's session, we are going to start with a absolutely convergent and conditionally convergent series and the power series. Now, first of all, what is the absolutely or conditionally convergent? If sigma un is what is a given series, then it is said to be absolutely convergent if sigma mod of un is convergent. That means the mode series of original series is convergent, then sigma un is said to be a convergent. Secondly, when the series is said to be a conditionally convergent, if sigma un is convergent but sigma mod un is divergent, that means the given series is convergent but its mode series is divergent, in that case the series is said to be a conditionally convergent. Now, if sigma un is absolutely convergent, that means it is convergent. The theorem we have written is, if mode series is convergent, then original series is obviously convergent. Please remember this. And the note we have written is, if the convergent series is a positive term series, that means if the given series is positive term series and it is convergent, then it is absolutely convergent. Why? Because mode of un will be un. So sigma un is convergent. So therefore sigma mod un is also going to be a convergent. So please remember, if it is a positive term series and the original series is convergent, then its mode series is obviously convergent. Now we are going with an example. Determine the absolute or conditional convergence of the series sigma minus 1 raised to n into n square upon n cube plus 1. See, here un is minus 1 raised to n into n square upon n cube plus 1. So mod un will be n square upon n cube plus 1. We are going to eliminate the plus or minus sign. Now this un is of mod un is of the form algebraic form. Numerator is algebraic, denominator is algebraic. That means we have a polynomial divided by polynomial. So we are going to apply the comparison test. So take vn from by dominant power of un in denominator, dominant power of un in numerator, both we are going to take out and find out vn. So n square upon n cube, that will be 1 upon n. Now that will give you vn is equal to 1 upon n, and you have to find the limit of mod un upon vn for condition of comparison test by limit comparison. So un upon vn, if you are applying limit, then you will have a limit 1, correct? So that is non-zero finite, that is our condition. So condition is satisfied. Now sigma vn, that is nothing but sigma 1 upon n, is a p series where n raised to nothing, that means n raised to 1 is given. So p is 1 and p is 1, that's why sigma vn is divergent by p series. So sigma vn is divergent, therefore sigma mod un is also divergent by comparison test. That means mode series is not convergent. That means it is not absolutely convergent. Now you have to check the conditional convergent. For that we are going to check out whether the original series is convergent or not. Now since original series is the alternating series, minus 1 raised to n is given, that means it is alternating series. So mod un is n square upon n cube plus 1. Now mod un plus 1 is n plus 1 whole square upon n plus 1 whole cube plus 1. Taking the subtraction and simplifying all terms, that will give you, and if you are going to simplify all the terms, then that will give you n raised to 4 plus 2n plus 1 in another bracket n square minus 1 divided by n cube plus 3n plus 3n square plus 2 inside another bracket n cube plus 1. Now obviously this term is greater than 1. Check out by putting n is equal to 1, 2, 3. So first all terms are positive, and that's why this series is numerically decreasing. Now the limit of un. If you are finding the limit to mod un, then it will be a limit n tends to infinity n square upon n cube plus 1. So n cube common out from denominator, that will give you 1 upon n into 1 plus 1 upon n cube. Now 1 upon infinity will be 0. So you will have 0, and that's why this limit is 0. So both conditions are satisfied. Thus given series is numerically decreasing and the limit of nth term is 0. So by Leibniz test, sigma un is convergent. That means original series is convergent, but sigma mod un is divergent. That means this given series sigma un is conditionally convergent. Okay. Same manner, we are going to check out one another example. Determine whether the series sigma cos n upon n square, that means cos 1 upon 1 square, cos 2 upon 2 square, cos 3 upon 3 square, and so on, is convergent or divergent. Now see, this given series is not an alternating series, because if you are going to find out the value of cos 1, then cos 1 is positive. 1 is considered in a form of radian. Same manner, cos 2 is going to be negative, cos 3 is also negative, and cos 4 is also negative. That means first term is positive, then 3 terms are going to be negative, then again 3 terms are going to be positive, then again 3 will be negative. So that is not alternating series. So you cannot apply the Leibniz test. Secondly, you have to test the convergence. So what we are going to do, we are starting with a mod un. Now we are already aware of mod cos n upon n square, but mod cos n has a maximum value 1, because cos has a range from minus 1 to plus 1. So mod cos n has a maximum value 1. So mod un will be less than or equal to 1 upon n square. Now it is less than or equal to 1 upon n square. So our Vn is 1 upon n square. So we are going to use the comparison test. For that, sigma 1 upon n square, that is sigma Vn, V is a P series with P is equal to 2. Now P is 2. So P is 2, that's why this series is convergent, because 2 is greater than 1. Now sigma Vn is convergent, so sigma mod un is obviously convergent, correct, by comparison test. So sigma mod un is convergent, and since sigma mod un is convergent, so by our condition of absolute convergence, if mod series is convergent, that means the given series sigma un is absolutely convergent. And you are already aware of, if the mod series is convergent, that given series is absolutely convergent, that means the series is convergent, because we have written the theorem. That's why the given series is convergent by theorem, correct? Now we are going on to the power series. Now see, up to here we have seen all the topics where whatever the series are given, they are given in some numerical form, correct? But now we are starting with a power series. That means now we are starting with the variable series. Here the series of the form sigma an into x minus a raised to n, where n is running from 0 to infinite. That means a0 plus a1 into x minus a plus a2 into x minus a whole square, and so on, so on, so on. See here, x is a variable, correct? Because you don't know what is the exact value of x. X can have any value from real line, correct? A x minus a, where a small a is called a center of a series, or you can say that series about that point x is equal to a. Okay, please remember this. And ans are any reals. That means an has any real value, which we have seen in a simple form, whatever the series we have written, such as an has any value. So please remember, here x is variable. So now the convergence is depending on the values of x. For different values of x, your series is going to be either convergent or divergent. So it is dependent on the values of x. Here we have written one simple example, sigma n running from 0 to infinity, x raised to n upon n factorial. That is nothing but 1 plus x upon 1 factorial plus x square by 2 factorial plus x cube by 3 factorial, and so on. Okay, and this series is a series in powers of x. That means the center of a series is a 0. Okay, please remember this thing. Now starting with one example, test the convergence of a series 1 upon 1 into 2 into 3 plus x upon 4 into 5 into 6 plus x square upon 7 into 8 into 9 plus dot dot dot, where x is greater than 0. Now you have already given that x is greater than 0. That means half of real line is given. So what we are going to do, un, we are starting with a un. So first write down un. Un is nothing but x raised to n minus 1. Correct? If you are starting with n is equal to 1, then you have to write down into form of x raised to n minus 1. If you are starting with 0, then you have to write it in a form of x raised to n. It is depending on you. Wherever you have to start with, you can start with that n. So un is equal to x raised to n minus 1. Now for denominator, we are starting with the first term of denominator. That is nothing but 1, 4, 7 and so on. So that is your arithmetic series with a difference 3. So we are, if you have to find out the nth term, then it will be a plus n minus 1 into d. So that's why a is nothing but 1 and d is nothing but 3. So that will give you, if you are putting the values, then you will have 3n minus 2. Same manner, second term, if you are going to consider, then that will give you the value 3n minus 1. And if you are going to consider only the last term, then 3, 6, 9, that means it is nothing but it is a 3n. So your un is x raised to n minus 1 upon 3n minus 2, 3n minus 1, 3n. That means un plus 1 will be x raised to n upon 3n plus 1, 3n plus 2, 3n plus 3. Now applying the ratio test. See, at the time of ratio test, we have already discussed that either you can find un plus 1 upon un or you can find un upon un plus 1. Only the conditions are going to be changed out according to the ratio. So we are starting with un upon un plus 1 and simplifying that terms. From the numerator, we are going to common out n from each bracket. So you will have n common, n common, n common. That means n cube is common out from numerator, n cube is common out from denominator. And that will give you the simplified form 3 plus 1 upon n into the another bracket 3 plus 2 upon n plus 3 upon n divided by 3 minus 1 upon n, 3 minus 2 upon n into 3 into 1 upon x. Now x raised to n minus 1 and x, that will give you the remaining part x. Now apply limit to the un. If you are applying limit to the un, then 1 upon n has a value 0. So you will have a final answer 3 into 3 into 3 divided by 3 into 3 into 3 whole into 1 upon x. That means 3 will be cancelled out and you will have only 1 upon x. So if you are starting with the conditions of a ratio test, then since you have taken un upon un plus 1, so in that case, if the limit is greater than 1, then the series is convergent. That means 1 upon x is greater than 1, then the series is convergent. That will give you x is less than 1, then series is convergent. And since x is already greater than 0, so 0 is less than x is less than 1, then the series is convergent. Same manner for 1 upon x is less than 1, then the series is divergent. That means x is greater than 1, then your series is divergent. And for x is equal to 1, your test fails. In that case, we are going to apply one another test. So put x is equal to 1 in un. Then your un is reducing in the form of 1 upon 3n minus 2, 3n minus 1 and 3n. This is nothing but this is a polynomial function. As we have seen, we are going to apply the comparison test because of numerator and denominator both are algebraic functions. So we are going to take a dominant part from numerator, dominant from denominator, and that will give you Vn is equal to 1 upon n cube. And now if you are going to apply limit to the un upon Vn for limit comparison test, then it will be a limit n tends to infinity n cube upon n cube into 3 minus 2 by n, 3 minus 1 by n into 3. So n cube will be cancelled out. Here we have used simplified form of un. So n cube will be cancelled out and you will have final limit 1 upon 27. Now 1 upon 27 is a non-zero finite number. So if you are to apply the comparison test, then sigma Vn is a p series with p is equal to 3 greater than 1. So by p series sigma Vn is convergent and sigma Vn is convergent. That's why your sigma un is also convergent. So sigma un is convergent for x is equal to 1. Okay, that means now what you have as a condition, for 0 less than x less than or equal to 1, your series is convergent, and for x greater than 1, your series is divergent. Correct? So see, here we have discussed three partitions of real line, half of real line. From 0 to 1, 1 is included. For that values of x, your series is convergent, and from 1 to infinite, your series is going to be divergent. That means if you are taking any value greater than 1, then this series is going to be divergent. Now, going with one another example, test the convergence of a series. Sigma n is running from 0 to infinity, n plus 1 upon n plus 2 whole raised to n into x raised to n, where x is greater than 0. Now see, first we have applied the ratio test. Now we are going to apply the root test, because whole raised to n is already here. So un is nothing but n plus 1 upon n plus 2 whole raised to n into x raised to n. So each term has a power n. So we are going to apply the nth root. That will give you un raised to 1 upon n is equal to n plus 1 upon n plus 2 into x. And if you are going to apply limit to the nth root of n, then you will have limit n tends to infinite, un raised to 1 upon n is equal to limit n tends to infinity 1 plus 1 upon n divided by 1 plus 2 upon n into x. We have simplified un, and now apply limit, that will give you the limit x. So here x is greater than 0, that's why now your condition is depending on the conditions of root test. According to root test, for x, whatever the limit is less than 1, then your series is convergent. So x is less than 1, then your series is convergent. X is greater than 1, then your series is divergent. And for x is equal to 1, test fails. Test fails, that means we are going to apply another test. So what you have, un is equal to n plus 1 upon n plus 2 raised to n. Now we are going to, since we are already aware of this is a simple power series, so what we are going to do, we are going to divide numerator and denominator with n. So it will be of the form 1 plus 1 upon n divided by 1 plus 2 upon n whole raised to n. So separating the numerator and denominator and applying the limit, that will give you limit n tends to infinite, un is equal to limit n tends to infinity 1 plus 1 upon n raised to n divided by 1 plus 2 upon n raised to n. Now numerator is obviously in the standard form. For denominator, we are going to multiply and divide with 2 in power. That will give 1 plus 2 by n raised to n by 2 whole raised to 2. So both the limits are going to be form of e. So you have e upon e square, and that will have a value 1 upon e. So un has a limit non-zero. So by test of divergence, un is going to be divergent for x is equal to 1. So now for your series, your condition will be of the form, for 0 less than x less than 1, the given series is convergent, and for x greater than or equal to 1, your series is going to be divergent. That means from 0 to 1 series converges, and for greater than or equal to 1 series is diverges. These are the all topics we have covered out. If you have any query or any doubt regarding this topic, then please feel free to contact me. Thank you.